Okay, now in this talk, let us see some more examples of a complete metric space, and we will also see some metric spaces which are not complete with respect to some metrics, or we will see that some spaces are complete with respect to one metric, but it is not complete with respect to other metric. So before going to that example, let us see here is very important space, that is your LP space. So in the LP space, as you know that we have seen that LP space is the space of sequences xn of real or complex numbers such that the summation I runs from 1 to infinity mod of xk raised to the power p is finite. And with respect we can see that dpxy is equal to summation k runs from 1 to infinity mod of xk minus yk raised to the power p whole raised to the power 1 over p, where x, y are the sequences xn and yn in LP. Okay. So the LP space with respect to this metric dp is a complete metric space. We have already proved that it is a metric. So LP with this dp metric is a metric space, but we will have to prove that it is complete. So this is a complete metric space. Now to verify that this LP space with respect to dp metric is complete, we will have to prove that every Cauchy sequence in LP space is convergent in it. Okay. So let us take xm be a Cauchy sequence in LP. Keep in mind, xm is the sequence of sequences, because LP is the space of sequences. So this is the sequence of sequences. So each term of this sequence is a sequence in LP space. Okay. So this is a sequence. Okay. And each term of this sequence is a sequence. So let this be a sequence. Then xm would be a sequence like this, x1m, x2m and so on. Okay. And so you can say that we can write, here is this, we can write x km, and k is the natural number, such that the mod of this, because this is the sequence in LP space, so mod of this, okay, the summation of k runs from 1 to n x k m mod raised to the power p is finite. So then the sequence is Cauchy. Here is the very important point, is that as we have seen in the case of Rn, so here is also, this is a sequence of sequences and each element of the sequence is of the form this one, and because this is a sequence in LP, so a sequence in LP satisfies this condition, so it must satisfy this condition. Okay. Then for each epsilon positive, because xm is a Cauchy sequence, so for each epsilon positive, there exists a positive integer n such that dpxm and xn is equal to summation I runs from 1 to infinity mod of xkm minus xkn raised to the power p whole raised to the power 1 over p. This is less than epsilon for all mn is greater than n. Okay. And now, as we have seen before, you can take 1 over p both the side. So this term is less than 1 epsilon raised to the power p. Okay. And because the summation is less than epsilon power p, and therefore the each term, okay, is less than epsilon, each term is less than epsilon raised to the power p, and therefore this p. So this you will get xkm minus xkn mod is less than epsilon. Okay. same as we have seen in the case of Rn. So you will get, and then this is what? This is a sequence, okay, this is a sequence of numbers, because it is a sequence of real or complex. So this is a sequence of real or complex number. That is to say, this is a sequence of, this is a Cauchy sequence in case, Cauchy sequence of real or complex number. And we have seen that whether K is R or C, in both cases it is a complete space. So it converges in K. And suppose that, assume that let xmk converges xk as m tends to infinity. Now using this limit, we define for x is equal to, for here is 1, so here is 1, here is 2, then here is 2. So we can define x is equal to x1, x2 and so on. Okay, then we will have to show that this x, this is a sequence, is nothing but is an element of LP, and xm converges to x. So now from this one, okay, we can take the square both the side. We take this pth power both the sides, so we will get this is less than this one. Okay, for all mn and all L runs from 1 to so on. And then we can take n tends to infinity. Then we will get this one. Why it is so? Because here is this converges to xk. Okay, this converges to xk. So as n tends to infinity, that term tends to xk. So we will have this one. Now you can see that this is a sequence. So this term, this is a monotonically increasing sequence which is bounded above and therefore has a finite limit. Okay, so this is the finite limit which is less than or equal to e raised to the power p. So this is less than or equal to s, and therefore this is less than or equal to epsilon raised to the power p. Now here we will have to use the Minkowskian inequality. So by using the Minkowskian inequality, we can write this from here. This term is less than or equal to, here you can add this term and subtract this one. So this is less than or equal to this one. Okay, so this is less than epsilon y, so this is bounded. Basically this is bounded and this is bounded, so this must be bounded, and therefore x whose elements are x1, x2, xk and so on. So this means that x is an element of LP space. Now we have to prove that this is. So from the inequality, this one we can write dp xm x is less than epsilon for all m is greater than n, which implies that xm converges to x. Okay, so xm converges to x and x is an LP, and therefore LP is a complete metric space. So this is the way to prove that the LP is a complete metric space. Here is the, in this one or even in the next exercise or in the previous one, the important thing is that we are considering the sequence in LP space, or in the next example we will consider the sequence in the L infinity, the space of bounded. So it would be the sequence of sequences. Okay, and the sequence of sequences, and the sequences, the term of the sequences are real numbers. Okay, and if they are converging to some point, then the sequence will converge to the it's a component wise, you can say, to the component of the x1k converge to x1, and then x2k converts x2. So we will have a point, I will have a sequence, and that sequence is your x in L infinity space. So that is a little bit you see, you can say that it is not confusing, but you have to be very careful over here. Let's see, here is next example. Next example is the space of all bounded sequences. Okay, also bounded sequences mean x, k, space of all bounded sequences of real or complex number. So this is the space such that mod of xk is finite with the sup metric dxy is equal to supremum of xk minus yk. Okay, where x and y are the sequences in L infinity, then this L infinity is a complete metric space. We have seen that it is a metric space, but it is a complete metric space. So again, we will prove that we can verify that it is how it is a complete metric space. Again, the same technique as we have used in the previous verification, that we consider a sequence of sequences. So xm, let xm be a Cauchy sequence in L infinity. So this is what, again, this is a sequence of sequences of real or complex numbers. So this is a Cauchy sequence where xm is equal to x1m, x2m and so on. Or you can write this is equal to xkm and k in natural number, such that the mod of the supremum of mod of this is finite. So then, because xm is a Cauchy sequence, so for each epsilon positive, there exists a positive integer n such that this thing holds good. Then that is to say dxm xn, which is equal to this thing by the definition of the sup metric, and this is less than epsilon for all mn is greater than n. And thus you can see that because the supremum of this is less than epsilon, so each term must be less than epsilon. So this term is less than epsilon for all k. It means what? It means that for all k, it means that this is a sequence of real or complex numbers, or this is a sequence, this is a Cauchy sequence in k. Okay, from here this is a Cauchy sequence in k. K means set of integers, set of complex numbers or set of real numbers. So in any case, whether it is a set of real numbers or complex number, both are complete. So this k is complete. So this will converge to some point. Let us take xkm converges x converge to xk as m tends to infinity for all k. Okay, using this limit, okay, if here is 1, so we will get 1. Here is k is equal to 2, we will get x2. x3, we will get x3. So then from there x1, x2, we can form x is equal to x1, x2, x3. Okay, and we will prove that this x is nothing but it is a sequence in L infinity, and we will prove that xmk, this sequence converges to this point x. Again, same as in the previous case, we can take a limit as n tends to infinity over here. So here is you will take limit tends to infinity, then this will tend to xk. So we can write this is less than or equal to xk for all m is greater than and k runs from 1 to infinity. Now since xm, okay, is a sequence, xm is this sequence, xm is this sequence. So this is a sequence. There is a real number m such that this the terms of this is less than or equal to nm for all k, and therefore we can write mod of xk is equal to, you can add this term and subtract this term, and then you use the triangular inequality, we will get this one. And this is less than epsilon and this is less than nk. So this is less than or equal to xk. And this inequality is true for each k, and the right hand side is independent of k. So here this is independent of k. So it means that this sequence is a bounded sequence of real numbers. Okay. So it means what? X is in L infinity, because L infinity is what? L infinity is the sequence of a sequence of real or complex numbers, bounded sequence of real or complex numbers. So this is real sugar. Now from here we can take dxy dxmx. Okay, this is equal to the, you can take the supremum of this one, which is equal, less than or equal to epsilon. So this is less than epsilon, so you can take another epsilon. So this is less than epsilon. So it means that the xm converges to x, and x is an LP, and therefore LP is a complete space. So this way we can prove, or we can verify that L infinity, LP, Rn, Cn are complete spaces. Okay, now let us take another example. So we take the space of all continuous real valued functions defined on the closed interval AB, that is CAB, with the sup norm. Sup norm means d infinity fg is equal to supremum over t in closed interval AB mod of f of t minus g of t. So with respect to sup norm, with respect to this norm, we say that or we will see that CAB is a complete space or a complete metric space. Again, to prove that this is a complete metric space, we will have to prove that every Cauchy sequence in CAB is convergent in it. It convergent to a limit point in CAB. So let us take Fn be a Cauchy sequence in CAB. Then by the definition of the Cauchy sequence, for each epsilon positive, there exists a positive integer n such that d infinity Fn is equal to supremum of mod of Fmt minus Fnt is less than epsilon for all Mn is greater than capital N. Okay. So because the supremum here is less than epsilon, so this term is also less than epsilon. That is, so we can say that, so we can take the supremum is, so we can take then for any fixed t naught. So for any fixed t naught in the closed interval, this fm t naught minus fn t naught mod is less than epsilon or all mn is greater than capital N. It means what? It means that this is what? This is fm t naught. Okay, now we are fixing t. But this is what? This is the sequence. Fm is the sequence of functions from the closed interval 0 AB to R. So this is a real number. Okay, this is a real number. So it means that this is a sequence. So this is a Cauchy sequence of real numbers. So this is the Cauchy sequence of real numbers, and real numbers is complete, and therefore this will converge to some point. So suppose that f and t converges to f of t naught as n tends to infinity. In this way, we can associate to each t in AB a unique real number f of t. Thus, we have defined a function f with domain AB. Okay, so we have defined a function f with the domain AB. Now we show that this f is nothing but it is an element of CAB and Fn converges to f. Okay, so from here you can see that because the supremum of this is less than epsilon, and therefore this term mod of Fmt minus Fnt is less than epsilon for all Mn is greater than n, and for all t in the closed interval 0, 1. Now we take n tends to infinity. So if n tends to infinity, and we see that this, okay, because this is the sequence of real numbers, so this converges to f of t. So this will converge f of t. So this here is f of t. Now to show that f is continuous, okay, we consider any t naught in AB and any eta is greater than 0. Okay, because now instead of epsilon we are taking eta. So according to the here preceding paraphrase, there exists a positive integer n1 eta such that fmt minus fnt is less than epsilon by 3. So here is this is epsilon by 3 for all n is greater than n1 eta and all t is in the closed interval ab. This is how it is true, because from this thing. Okay, so we will get this one. And now we take n is greater than or equal to n1 eta. Then we see that mod of f and t minus f of t is less than eta by 3 for all t in the closed interval 0. By continuity of fn, we can say that we obtain a delta positive such that fn t minus fn t naught, okay, fn t minus t naught is less than eta by 3 whenever the mod of t minus t naught is less than delta. And then from these two inequalities, we will get mod of f of t minus f of t naught is less than or equal to mod of, so by using the triangle inequality, we can say that mod of f of t minus f of f and t plus f and t minus f and t naught plus f and t naught minus f t naught. So this is less than eta by 3, this is less than eta by 3, this is less than eta by 3. So this is less than eta whenever mod of t minus t naught is less than delta, and therefore f is a continuous function, and so it belongs to CAB. Now from this, okay, from this 2.6 we can see that the supremum of this is less than epsilon. So the supremum of this is less than epsilon. It means that d infinity fm f is less than epsilon. It means what? So this is less than epsilon for all m is greater. It means fm converges to f. So fn converges to f, and f is an element of CAB, and therefore CAB is complete with respect to the supernorm. So here is a very important result. You can see that CAB is a complete metric space with respect to the supernorm. Now we have the another example. Take the C01 set of all continuous real valued continuous function defined on the closed interval 0, 1. This CAB, okay, or C01 as a particular, we are taking C01, is not complete with respect to the integral norm. It is complete with respect to the subnorm or with respect to the d infinity norm, but it is not complete with respect to the integral norm or d1 norm, which is defined in this way. That is d1 fg is equal to the integral from 0 to 1 mod of f of t minus gt dt for all fg in C01. So C01 is a complete, C01 is complete with respect to the subnorm or d infinity norm, but it is not complete with respect to the integral norm or d1 norm. Let us verify this fact. So we can verify this fact. So we will have to produce some example. Okay, to produce the example, we are considering a sequence Fn, n is greater than or equal to 2, be a sequence of functions in C01, which is defined in this way. That is, f and t is equal to 0 if t lies between 0, 1 over 2 minus 1 over n, and t lies between 1 over 2 minus 1 over n and 1 over 2. Then the value of f and t is equal to nt minus 1 over 2n plus t. And the value of the function is 1 when t lies between half and 1. Okay. So this way, let us see that, let us check whether this sequence of functions is a Cauchy sequence or not. So we claim that this is a Cauchy sequence, but does not converge in C01 with respect to D1 metric. So let us see whether it is a Cauchy sequence. So let us take d1 fm fn. Okay. So 0 to 1 we can write 0 to 1 fn, and now because the f and t is divided into 3 intervals, so we can divide into 3 intervals. Okay. So in the first interval it is in the first one it is 0. So this is 0, this is 0. So it is 0. So forget about this. So we have left only this one. So in the first one, from 1 over 2 minus 1 over n, 1 over 2 minus 1 over n to 1 over 2, the value of the function is this one, f and t. And then here is from 2 to 1. So this is from 1 over 2. Okay, so 1 over 2 to m. So this is less than or equal to fmt plus this one. Okay. Okay, so for if it is in this interval, it is 1, it is 1. So it is equal to 0. In this interval, it is 0. So we have taken only this interval. So we have this one. And now we can put the value of fmt is this one and fnt is equal to this one, and then we can calculate. So we will have this one. As mn tends to infinity, this tends to 0, and therefore fn is a Cauchy sequence. Okay, so we can prove that it is a Cauchy sequence. So fn is a Cauchy sequence, and now the measure d1 fm fn is the area of the triangle in the following figure. So as I mentioned, because this is the integral norm, so this is the area. So this is the graph. So you see here is from here to, so in this interval 0 to 1 over 2 minus 1 over n, and then from this interval, this is the your function fn, and then after 1 it is 1, it is equal to 1. So this is the graph of the function is this fnt is this one. Okay, but now you can see that d1 fm fn, so dfm, so here is you can take from here and then go up to here, this one. So this is your fn, and now from here to here, and you go this way, and then this is your fm. So basically d1 fm fn is this area. This area represents, so d1 fm fn represent the area of the shaded triangle, this area. Okay. Now we have proved that the fn is a Cauchy sequence. We have to prove that it is not convergent. Okay, so not convergent in C01. So for that, suppose that there is a function f in C01 such that fn converges to f, that is d1 fn f converges to 0. Okay, but d1 fn f, okay, it is from, because the definition of fn, so it is equal to 0 to 1 over 2 1 minus n mod of f of t dt plus 1 over 2 minus 1 over n 1 upon 2 fn t minus f of t dt, because in this interval the value of fn t is equal to 0. So here is 0, and here is from 1 to half, the value of fn t is 1. So here is 1 minus f of t. Now since the integrands are non-negative, okay, these are all great mod of this, here is mod, here is this, so all are non-negative. So is the each integral on the right hand side of this, and since this converges to 0, because we are assuming that this converges to 0, we must have that the limit as n tends to infinity, this must be equal to 0 and this term must be equal to 0. Okay, so if we are taking this is equal to 0, and since f is continuous, because f is in C01, we are assuming that we must have f of t. The value of f of t when t lies between 0 1, it is equal to 0, and when it is lies when 0 1, it is equal to 1, and 1 half and 1, it is equal to 1. So f of t is equal to 1, but this function is not continuous. So, therefore, f is not continuous, which contradicts to our assumption that f is continuous, and hence C01 is not complete. So, this way is we have seen that the C01 is complete with respect to the metric D1 or with respect to the with respect to the D infinity metric or with respect to the sup metric, but it is not complete with respect to the integral metric. So, this you keep in mind. And before closing this section, okay, so in the next talk, we will see some more examples. Okay, so I stop over here. Thank you very much.